Chapter number 1, Metric Spaces. Before going into the definition of metric spaces, let me speak of the distance function. In calculus, we study different functions which are defined on the set of real numbers or the real line. At several occasions, we have to use the distance function. For example, we use the distance function in the limit processes. As an example, consider the continuity of the function f of x at the point x is equal to a, where a has been taken from the set of real numbers, or it is taken from a subinterval of real line. So, from the definition of continuity in calculus, we have this function f of x continuous at point x is equal to a if this limit holds, limit x approaches to a applied on f of x is equal to f of a. There is another definition of the continuity of a function, and that definition is called the epsilon delta definition. According to that definition, a function f of x is continuous at the point x is equal to a if for every epsilon greater than 0 there exists a number delta greater than 0 such that absolute value of f of x minus f of a is less than epsilon whenever 0 is less than or equal to absolute value of x minus. Chapter number 1, Metric Spaces. Before going into the definition of metric spaces, Chapter number 1, Metric Spaces. Before going into the definition of metric spaces, let me speak of the distance function. In calculus, we study different functions which are defined on the set of real numbers or the real line. At several occasions, we have to use the distance function. For example, we use the distance function in the limit processes. As an example, consider the continuity of the function f of x at the point x is equal to a, where a has been taken from the set of real numbers, or it is taken from a subinterval of real line. So, from the definition of continuity in calculus, we have this function f of x continuous at point x is equal to a if this limit holds, limit x approaches to a applied on f of x is equal to f of a. There is another definition of the continuity of a function, and that definition is called the epsilon delta definition. According to that definition, a function f of x is continuous at the point x is equal to a if for every epsilon greater than 0 there exists a number delta greater than 0 such that absolute value of f of x minus f of a is less than epsilon whenever 0 is less than or equal to absolute value of x minus a less than delta. So this definition is given in the courses of calculus when you study the continuity of a function. So here in this second definition, we have used the distance function twice. First, we have used it here. The absolute value of x minus a is actually the distance between the point x is on the set of real numbers, or it is on the real line. Let we say that x is here Absolute value of x minus a is the distance between x and a. Let we say that a is here. Then the distance between this point and this point is absolute value of x minus a. And we can write it as, if we take the distance function as d, then it is applied on 2 points, x and a. So it is the function of two variables, x and a, where x and a, they both are taken from the set of real numbers or from the real line. Similarly, absolute value of f of x minus f of a is also the distance between f of x and f of a. So generally, when we are in calculus and when we are taking the distance function, if we take 2 points x and y from the set of real numbers, then we say that the distance function is given by d of x and y, and it is equal to absolute value of x minus y. Note that the distance function cannot be applied on single point, because whenever you are taking the distance, you must have 2 points. Therefore, the distance function is a function of two variables. So when we are in calculus, we study different functions defined on real line. But when we come in functional analysis, we have the functions defined on more general spaces. That we call any one of the space as the space X. This space is an abstract set. It means that the nature of the elements of X is unspecified. Similarly, the distance function when we are in calculus is defined on real line. But the distance function when we come in functional analysis is defined on the space X. And the distance function in the functional analysis satisfies only a few of the most fundamental properties of the distance. And those properties are called the metric axioms. And these metric axioms will be given in the definition of the metric space. So let me move on to the definition of the metric space. In the first topic of section 1.1, we will study the definition of metric space. A metric space is a pair and this pair is x d, and as we know that X is a space and d is the distance function on X. Distance function on X, or defined on X. And this distance function is also called the metric. Also called metric on X. Such that for every, take 3 points from X, small y, and small g from X, such that this metric D satisfies the following 4 axioms called the metric axioms. Number 1 is called M1. The first axiom of metric is that D is real valued finite, that is, it should not be infinity, and non-negative. It should not be negative because it is satisfying the properties of distance, so the distance cannot be negative. In other words, we say that D is greater than or equal to 0, and since D is real valued, so we can write it as it has the domain X cross X, which denotes the set of ordered pairs of X, and it gives the results into the set of real numbers because it is real valued. This was the first property. The second property is M2, and it says that distance of X and Y, if we take any 2 points X and Y and we apply the distance on them, then this is 0 if and only if these 2 points were identical. So this is the important property. If you are asked in the case of set of real numbers to find the distance between a point 5 and another point, it is again 5, then since these 2 points are at the same location, therefore there is no distance between them. The distance between them is 0. And the third property is called the symmetry property. It says that distance between X and Y is same as the distance between Y and X. D of xy is equal to D of y and x. So in the case of real numbers, if you're asked to find the distance between 5 and 8, then this distance is equal to 8 minus 5 absolute value, which is equal to absolute value of 3, and it is equal to 3. Similarly, if you are asked to find the distance between 8 and 5, then this distance becomes absolute value of 5 minus 8, and this is equal to absolute value of minus 3, and according to the definition of absolute value, this is equal to again 3. So this was so simple to understand. The next property is very important property. The third property is called the symmetry property. The fourth and the last property is quite important, called the triangle inequality. It says that d of xy is less than or equal to d of xz plus d of zy. To understand this important property called the triangular inequality or triangle inequality simply. To understand this inequality, draw a triangle with the points. This point is x, this point is y, and the last point is z. Form a triangle, this one, with the vertices x, y, and z. This line from y to z is the distance d of y and z, definitely. Similarly, this line is the distance between x and z, while this line is the distance between x and y. Now apply a property of triangle that the length of any side of a triangle is always less than or equal to the sum of the lengths of other two sides. So this is the length of one side, and on the other hand we have the sum of the lengths of other two sides. So the length of one side of the triangle is always less than or equal to the length of sum of lengths of other two sides. So this was very simple and easy to understand. So these are four important axioms of the metric space which are necessary to be satisfied if the given space is a metric space. So this completes the concept of the metric space. Now we will generalize the triangle inequality and we will get a generalized triangle inequality. First, instead of 3 points x, y, and z, we will choose 4 points x1, x2, x3, and x4. First, we have to form a triangle. So we have this triangle and apply the triangle inequality here. This line is the distance between x1 and x4. So from triangle inequality we have distance of x1 and x4 is less than or equal to the other two distances, distance of x1, x3 plus distance of x3 and x4. So this was quite obvious. Now move to the next triangle, which has the vertices x1, x2 and x3. That is this one. And in this triangle you can again apply the triangle inequality. So by applying the triangle inequality on this triangle, we have distance of x1 and x3 is less than or equal to the other two distances, that is distance of x1 and x2 plus distance of x2 and x3. So put this inequality right here. D of x1 and x3 is less than or equal to d of x1 x2 plus d of x2 x3. So by putting this inequality here, we have, instead of d of x1 x3, we can put it less than or equal to d of x1 x2 plus d of x2 x3, and write the final term d of x3 and x4 as it is d of x3 x4. So this was the triangle inequality for these 4 points. Now proceed further and go to the point xn. The last point is xn, and the point just behind it is xn minus 1. So you have a new triangle, this one. So if you apply the distance property, the triangle property here, then you have d of x1 to xn is less than or equal to, look into the triangle, it is less than or equal to d of x1 xn minus 1, d of x1 xn minus 1 plus d of the other distance is the distance between xn minus 1 and xn. And again you have to break down this one as you did for the case of x1 and x3, and you have to form another triangle, and at that triangle you have to apply the distance property, and you have to proceed further so that you will get this to be less than or equal to d of x1 x2 plus d of x2 x3, and up to so on to the final term is d of xn minus 1 and xn. So this formula is called the generalized triangle inequality. Hopefully you may have understood it quite clearly. It was quite obvious. We have proved this formula now. Now we will go to the more general concept. Consider a subspace of X. Let Y is a subspace of X. It means that Y is a proper subset of X. Now you have a metric D, which is defined on X on its ordered pairs, and it gives its values in the real line. Apply this metric D on Y. So it means that now you are applying this metric D on the ordered pairs of Y. Y cross Y, and the results are again in the set of real numbers. This metric is the restriction of this metric, because this was the greater metric and it is applied on the ordered pairs of the greater space X. But this metric is now restricted to the ordered pairs of the subspace of X, and this metric is called the restriction of this matrix, is this metric D, and we will denote it by D bar. So D bar is equal to the distance function or the metric D on X, but it is now restricted to the ordered pairs of the subspace X. And we call this new metric D bar as D bar is called the metric induced in inverted commas. This metric is induced on Y, because now this D bar is being applied on Y. And who is inducing this metric? The metric D is inducing it on Y. So this was our first lecture. In the next lecture I will give you the examples of the metric spaces by proving all of the 4 properties of the metric. Thanks for watching. So as a first example we have the real line. The real line is actually the set of real numbers. You have to show that this real line is a metric space with a usual metric defined on it. Now what is the usual metric? Usual metric is given by D of X and Y is equal to absolute value of X minus Y. So it simply means that the usual metric is the distance between any two elements of the given space. So here x and y are the members of the real line or the set of real numbers. So let me prove that this real line with this metric is a metric space. All what you have to do is you have to check that this usual metric satisfies all four properties of the metric that we have learned in the previous lecture. The first property is the M1 property. First property of the metric. In this property you have to check whether the given distance function is real valued, non-negative and finite. Now since x and y are real numbers, so their difference is a real number. And when you will take the absolute value of a real number, then the result is again a real number. So it simply means that absolute value of x minus y, that is the given distance function, is real valued. Next you have to check that it is non-negative. Yes, it is non-negative because whenever you take the absolute value of a negative number, you have a positive number back. Similarly, if you take the absolute value of a positive number, you have again the positive number back. So it means that the absolute value is always positive. So this means this distance function is positive and it is non-negative. So we have d of x and y that is equal to absolute value of x minus y. This is always greater than 0 or it is equal to 0. And it is also finite because all of the real numbers are finite. So their difference is finite and their absolute value is therefore finite. So it means that the property M1 is easily satisfied. So M1 is satisfied. The reason that you will write down here is that you will write that the absolute value is always non-negative, real valued and finite. Therefore, M1 is satisfied. Now let me move on. The second property, M2 property. In this property, you have to prove that d of x and y it is equal to 0 if and only if x is equal to y. Or in some text it is also written that d of x and x is equal to 0. So these both statements mean the same things. So since there is if and only if, therefore you will also have to prove a converse of it. So first let d of x and y is equal to 0. So let d of x and y is equal to 0. It means that put the value of d of x and y that is equal to absolute value of x minus y, and since it is equal to 0 according to our supposition, and now you have to apply the definition of absolute value, and according to the definition of absolute value we have absolute value of x, it is equal to positive x if x, that is the number inside the absolute value, is positive. And the answer of this thing is equal to 0 if x were 0. Similarly, the answer is multiplied with a negative. We have minus x if x is negative. For example, if we have negative of absolute value, then according to this definition, this minus 5 is multiplied with a negative, and we have back plus 5. So leave it aside and look at the central value. It means that the answer of the absolute value is 0 only if x is 0, that is, the number inside the absolute value is 0. So according to this definition, we have the number inside the absolute value, it is equal to 0. And if we add the additive inverse of minus y on both sides, that is plus y, we have x minus y plus y is equal to 0 plus y. Since y minus y and plus y, these are additive inverses of each other, therefore they cancel each other and we have an additive identity, that is 0, additive identity of real numbers. Similarly, on the right hand side, when the additive identity is added into a real number, then we have again that real number back. And from this, and again use the same property on the left hand side of the next step, you have x, and this is equal to y. So from d of xy is equal to 0, we have proved that x is equal to y. Now we will have to prove it conversely. Now we will suppose that x is equal to y, and we will have to prove that d of x and y is equal to 0. For this, you have to add minus y on both sides, and from this, x minus y is equal to 0. And take the absolute value on both sides. X minus y is equal to absolute value of 0, and we know that the absolute value of 0 is 0. And since absolute value of x minus y is equal to the given distance function, and we have proved that if x is equal to y, then d of x and y is equal to 0. So d of x and y, this is equal to 0 if and only if x is equal to y. So this was very simple. Let me move on to the property number 3. This is M3 property, in which you have to prove that d of x and y is equal to d of y and x, and this is called the symmetric property. So d of xy, it is equal to absolute value of x minus y. If we take a minus common, then we have inside y minus x. And again, by using the definition, the absolute value of minus x is equal to absolute value of x. Therefore, according to this definition, we have this thing is equal to, the negative sign is removed, and we have absolute value of y minus x. And this is equal to d of y and x. So it is easily proved that d of x and y is equal to d of y and x. That is the symmetric property holds here. Now you have to check that the fourth and the last property M4, that is the triangular inequality. You have to prove that this triangle inequality holds. For this, you have to let x, y, and z, they all belong to the set of real numbers. D of xy, it is equal to absolute value of x minus y. We can add and subtract z, so we have x minus z plus z minus y. So we have added and subtracted z without affecting the equality sign, and this can be written as absolute value of x minus z plus z minus y. Now you have to apply a property of absolute value. From calculus, you have learnt that absolute value of two real numbers a minus b, it is less than or equal to absolute value of a plus absolute value of b. It is very easy to prove it, and you may have proved in the calculus. So apply this property here. Now instead of a we have x minus z, and instead of b we have z minus y. So by applying this property right here, we have d of xy less than or equal to absolute value of x minus z plus absolute value of z minus y. What is x minus z? This is distance between x and z. So we have d of xy less than or equal to distance between x and y, that is d of x and y, sorry, x and z plus d of z and y. So it was the required triangle inequality. And we will write here that since all of the properties of metric are proved true, therefore the given space R is metric space. Since the metric d of xy satisfies all metric properties, so R is a metric space with metric or usual metric defined on it. Usual metric D on it. So hopefully you may have understood this simple properties. Next example is the Euclidean plane denoted by R square. The elements of this Euclidean plane are in the form of ordered pairs of real numbers. For example, if we choose x and y from the Euclidean plane R square, then definitely x and y are in the form of ordered pairs. X is the ordered pair of xi1 and xi2, and y is the ordered pair of eta 1 and eta 2, where xi1, xi2 and eta 1 and eta 2 are the real numbers. You have to prove that this Euclidean plane is a metric space with the metric defined on it is given by d of x and y is equal to square root of xi1 minus minus eta 1 whole square plus xi2 minus eta 2 whole square. And this metric is called the Euclidean metric, and it actually represents the distance between x and y. We know that if two points are in the form of ordered pairs, then their distance is given by this formula. So this can be explained with the help of a diagram. This is the point x, and this is the point y. The point x in the form of ordered pairs is xi1, xi2. Similarly, this point is eta 1, eta 2. The horizontal value of this point is xi1 and the vertical value is xi2. Similarly, the vertical value of this point is eta 2 and the horizontal value is eta 1. The line joining these two is the distance between them, and it is given by this formula, and we know this by we know it from the basic geometry that this formula is called the distance formula for the points this one and this one. So let me show that this satisfies all four properties of the metric. For property M1, note that since xi1 and eta 1 are real numbers, so their difference is a real number, and the square of a real number is a positive real number. So this quantity is positive and this is also a positive real number. So their sum is a positive number. So the quantity which is coming under the square root is positive, and the square root of a positive number is again a positive number. So it means that d of xy is greater than or equal to 0. And similarly, it is also finite because x and y are real numbers. xi1 and xi2 and eta 1 and eta 2 are real numbers which are always finite. Next, you have to show that the given metric satisfies the property M2. So you have to prove that d of xy is equal to 0 if and only
Lecture number 4. In this lecture, I will give you some of the
y.
interesting examples of the metric
So this is
spaces.
simple.
You will also have a first impression of how general
Suppose
is the
that
idea of a metric space is.
d of
So let we
x
begin.
and y is equal
The
to
first one is the sequence
So it
space,
means that
which
square
is
root
denoted
of
with L infinity. The elements of this space are the bounded sequences of the complex numbers.
plus
So
xi2 minus eta 2
let
whole square
x
it is equal
be
to 0.
a set of,
If you take the square on
all
both sides, you
bounded
get xi1 minus eta 1 whole square plus xi2 minus
sequences.
eta 2
Since we are going
whole
general,
square is equal
therefore
to 0
we
square,
have
that is
chosen
equal to
all of
0.
the bounded sequences of complex numbers.
Now this equation holds only if
xi1 is equal to eta 1 and xi2 is equal to eta 2, because since
let we
this
take two
quantity is
elements from this
positive and
set.
this quantity is also positive, therefore they can never become the additive inverses of each other, and therefore they cannot cancel each other. So the only choice that we are left with is that this xi1 should be equal to then this eta 1, so that these are same quantities and their difference is 0, and same is the case for
Such
this second
that,
quantity, and 0 plus 0 is again a 0. So we will say that this
since we
equation
know that
holds if and
X
only
is
if.
the set of all bounded sequences of complex numbers, so any element of this is a sequence of complex numbers. Let the sequence be
If and only if
the sequence of xi1,
xi1 is equal to eta 1
xi2,
and
xi3, and up
xi2 is
to
equal to
so on.
eta 2.
This is infinite sequence, and we can write it just
From this
simply
situation, we have x is equal to y because
xij.
x is equal to
xi1, xi2, and all of the elements of this sequence
xi1
are the complex numbers,
and xi2,
where j
and
is equal
since
to
y is equal to eta 1
1,
and eta
2,
2,
and up to so on. Since
and since eta 1 is equal to
X
xi1, so
is the
instead
set
of
of all
eta 1 we can
bounded
put
sequences of
xi1, and
complex
instead of
numbers,
eta 2
so
we
X
can
is a
put
sequence
xi2.
which should be bounded. So according to the definition of a
So
bounded
this
sequence,
implies that x is equal to y. You do not need to prove this conversely because you have already used if and only if.
absolute value of xij
Next is the property M3. If you want to prove it conversely, then you have to apply these concepts in the reverse. You have to apply these steps in the reverse direction. Next property is M3, and before this property you have to note that a minus b whole square is equal to negative of b minus a whole square. This square cancels this negative sign and you have b minus a whole square. So a minus b whole square is equal to b minus a whole square. Now you write your given distance function d of xy is equal to square root of xi1 minus eta1 whole square plus xi2 minus eta2 whole square. By using the property that I have just mentioned you, we have this thing is equal to eta 1 minus xi1 whole square plus eta 2 minus xi2 whole square. What is this? This is simply d of y and x. Thus d of x and y is equal to d of y and x. So the symmetric property holds here. The next and last property is M4, in which you have to satisfy the triangle inequality. For this you have to let z is equal to zeta 1, zeta 2. Let this belongs to r square. The triangle inequality can be proved here by using different properties, but I will choose a simple path. You have to make a diagram. This is point x, which is in the form of ordered pairs xi1, xi2, and this is the point y, which is the ordered pair of eta 1, eta 2, and this line joining them is d of x and y. You have to first draw the coordinate axis. Take a third point. The third point is z, which is equal to zeta 1 and zeta 2 ordered pair. Now you have to join these points to form a triangle. And next you have to apply the property of a triangle that the length of its any one of its side is less than or equal to the sum of lengths of other two sides. So you have to write that in triangle x, y, z. We have d of x and y is less than or equal to the sum of lengths of other two sides. This side is d of x and z, and this one is d of z and y. So we have d of x and y less than or equal to d of xz plus d of zy. So this is the required all four properties of the metric, and we see that these all four properties are satisfied. Thus the given Euclidean plane is a metric space. Next examples will be given in the next lecture.
Lecture number 4. In this lecture, I will give you some of the interesting examples of the metric spaces. You will also have a first impression of how general is the idea of a metric space is. So let we begin. The first one is the sequence space, which is denoted with L infinity. The elements of this space are the bounded sequences of the complex numbers. So let X be a set of all bounded sequences. Since we are going general, therefore we have chosen all of the bounded sequences of complex numbers. Let me take two elements from this set. Then such that since we know that X is the set of all bounded sequences of complex numbers. So any element of this is a sequence of complex numbers. Let the sequence be the sequence of xi1, xi2, xi3, and up to so on. This is infinite sequence, and we can write it just simply xij. xi1, xi2, and all of the elements of this sequence are the complex numbers, where j is equal to 1, 2, and up to so on. Since X is the set of all bounded sequences of complex numbers, so X is a sequence which should be bounded. So according to the definition of a bounded sequence, absolute value of xij is less than or equal to a real number. Let the real number be Cx. This is in accordance with the definition of the bounded sequence that you may have learned in the calculus or in the real analysis. If you have not learned that definition, please go to your course of calculus and search for the definition of a bounded sequence. So Cx is a real number. We will write that where Cx is a real number. This real number depends on the sequence, and it does not depend on the index or the dummy variable j equal to 1, 2, and up to so on, which depends on x, but not on j. Similarly, you can choose another element y equal to the sequence of complex numbers eta 1, eta 2, and up to so on, which can just be written as eta j, where j is equal to 1 and up to so on. Since it is bounded sequence, therefore eta j absolute value is less than or equal to a real number cy, where cy belongs to the set of real numbers and depends on y, but not on j. You have to prove that this space X is a metric space with the metric defined on X is given by, so we choose the metric defined by d of x and y is equal to supremum
of the
It
absolute
looks
value
like he
of
has
the
this just
difference
a natural
between
pace. It's
xij
decent
and
pace,
eta
53
j,
to 55 miles an hour for an off spinner.
where j is taken from the set of natural number. J is a natural number. We have to do this
Not there.
because j is equal to 1, 2, 3, 4
Player's gonna knock that
and
away.
so on. It simply means that j is a natural
It
number.
looked like it's intended to be an arm ball.
What is the supremum?
Seems
You must
up
be
rather
familiar
more
to
than
this
turning.
definition too,
Hope it
as
drifts
I
in.
have just
but
recalled you the definition of
it's
bounded
one of those
sequence.
things that
Similarly,
you don't get the length
I
right.
would like to recall you the
That's what
definition
happens,
of
you get crashed
the
away
supremum.
before.
For the definition
it
of
just-
supremum,
I
you
think
must
it
be
just needs to
familiar
keep
with the upper bound of a
A
set.
simpler strategy. 42
Note
for
that
one.
the absolute value of xij minus eta j, when j is a fixed number, for example 1, when j is equal to 1, then we have xi1 minus eta 2. Sorry, xi1 minus eta 1. Similarly, when we take j is equal to 2, then we get a number
Change the pace
xi2
slightly.
minus eta 2 and up to so on.
Sometimes things are overcomplicated.
So we can collect them and we can make a set with these values. And
Of course, that's been
then
20
you
years
have
of age.
to
I'm
take
gonna
the
bowl an
supremum of
absolute
this
jaffer
set.
every ball.
So what is the supremum? For this I will give you a very basic example. Consider that we have a set 1, 2, 3 and up to so on. We can see that there is no upper bound of this set. This set is open from the above. Similarly, if we take another set 1, 2,
I always remember
3,
asking John Embury,
4,
off spinner for England,
5.
real strong action, John. And he got picked for England, you tell
Curly
me, around about
brackets should be
24,
used
25 years of age. And then I asked him, when did you
for,
really know about
sets.
off spin? When did you understand it? And he said, when I was
You
about
can see
27,
that
I understand
there is
the
a
mechanics
real
of it.
number 6, which is
Well, he was
binding
he was
this, not
27,
binding,
28, I think,
which
when
is
he
the
first
upper
played.
bound of this set. Similarly, 7, 8, and 9, and up to so on. All of these
And
numbers are
then,
the upper
as you
bound
say,
of
strong
this
action,
set.
therefore
Let
he
me
could
call
then
this
play
set as set A.
first-class cricket for another decade after that, I think it was, give or
What
take.
is the
So if he played when he was
smallest
27,
upper
28
bound?
for England,
You
he'd
can
have had a
see
heck of a
that
grounding in county cricket.
5.1
Yeah,
is
I mean,
also
in those days
an
you
upper
played more
bound of
county
this
cricket,
set.
played more three-day cricket, and you had plenty of time
5.01 is
to
also
learn the
an
trade. It
upper
had
bound
Fred
of
Titmus here before him.
Similarly,
talk to and discuss.
5.0000001 is again an upper bound of
He had
this
Phil
set.
Edmonds at the
So,
other end as well.
by
Who was
definition, the
an
least upper
excellent slow
bound
left arm spinner.
is called the supremum of this set, and for this set,
Figures there,
this
64
element
test matches,
5, this is
47 wickets.
the supremum for this set. So by the definition, if we denote all of these elements by x, then supremum is always less than, let we call that supremum as m. It is always greater than or equal to
Mark Wood again, same field.
x. So this simply means the elements of this set are always less than or equal to the supremum. The only element that
Field
proves to be
change.
equal to this one,
Alistair Cook
the
is
supremum, is
trotting up
the
from
element
slip.
5. But not other elements can be equal
Short
to
in on the offside.
this one. If we choose x less than m, then it means that m is not the supremum. It is just the upper bound of this set.
Stuart Broad, he's galloping down to third man.
Similarly, we can also define the lower bounds, and the greatest lower bound is called the infimum of this set. So hopefully you may have understood the idea of the supremum and infimum from this definition. Next, you have to prove that this metric space x with this defined metric, this one d of x and y, is a metric space. So the question is, And before this, you may have to write that
It's a good
you have
leave.
to understand that this
42 for
underlying
one.
set X with this metric space, sorry, with this metric is called the sequence space L infinity. So we will say that the metric space is called the sequence space which is denoted with L infinity. Now you had to prove that this space is a metric space. Show that
Nicely played.
L infinity.
One of those as a batsman, you're just slightly against the spin, but full face of the bat. Catch it on the half volley.
Metric space with
On the full.
Full P.
the metric defined above.
And just beat mid on the right hand side. I'm hitting it straight.
So let me go to proving the properties of the metric spaces. The first property is M1. We have to prove that d of xy satisfies the property M1. Look at into the form of d of x and y. It is just equal to the supremum where j is a natural number, supremum of the set obtained from the absolute value of xij minus eta j. Note that xij
Another
and
belter.
eta j are complex numbers,
I think this is
so their
half
difference
volley.
could also be a complex number. But
Well, yeah,
when
this is
we
where
take
Don
its
Best will learn
absolute
about the
value,
precision needed
that is
at the
when we
highest
take
level.
its mod,
A half
then
volley or a full toss is a
this
half volley or a
modulus
full
is
toss and will get
always
treated
a
as
real
such.
number.
If you're
So
offline, you'll get
this
nudged.
set
These are
is
good shots,
the set
but we saw
that
the
is
full
obtained
toss
from
earlier. That's a
taking
full
the
half
absolute
volley.
value of xij
So no
minus
risk
eta j.
involved playing
The
through
set
that.
is
Good
the
shots,
real
but
number. So we get a set
slightly
of
a
real
miss with the
number.
bowling. That's
And
good footwork.
definitely the sum of that set should be
I mean, I don't mind the
a
fact that
real
Best is
number.
still using flight.
So
You know, the
it
obvious
is obvious
temptation is to
that
go
d
flat
of x and y
Stop
is
doing
a
that.
real
It's
number.
2 for 1 now.
Similarly, the absolute value is always greater than or equal to 0, that is non-negative. It is defined. Therefore, we can see that this metric satisfies the property M1 of a metric. So this implies, so after writing all of this information, you might write
Helmets
d of
and
x and
close.
y is greater than or equal to 0, and
Your
this
route there,
metric d of
offside on
x
his
and y
knees.
satisfies the property M1.
There'll be a picture of
Let
that.
me move to the property M2. In this property,
Three
you
here.
have to
This is a
prove that d
long,
of
long
x, y
chase.
is
There's
0
no mid off.
if
Who's
and
after it?
if
Ben Stokes.
x is equal to y. For
Yes,
this,
think about that.
you have to first
If you're a
suppose
politician,
that
you're very careful not to put yourself in a position for a photograph that can be misinterpreted or given a
d
caption.
of x and y is equal
That,
to
is
0
a
and put the
sub
value
editor's dream. If you're England captain on your
supremum
knees,
j member of the set of real
and
numbers,
you're just about in this case to lose the first test.
absolute value of
of summer,
xij minus
That's inevitably going
eta
to be a
j
caption
is
somewhere
equal to
tomorrow.
0. From this
It's a questionable
equation, you
tactic
have
anyway.
to take the concept
I know he did this in New
that
Zealand.
if
But that
the
was with the spinner,
supremum
and that was the
of
dying
a
moments.
number
And I
is
think
0,
if you're a
then
silly
there are
point
two possibilities.
to a pace
that
bowler. I mean, for instance, if you're
set
there
is-
for something that basically
The
pops
set
up off the
has only
glove or
one
the
element,
bat,
that is 0.
where the batsman has failed to
Or
control it,
the
you need
set
to be able to move,
has,
and you need to be
together
on
with
your
the 0,
feet.
it also have some negative values, -3, -2, and -1,
Were you ever on your
and
knees
0.
as England captain?
We can see that
metaphorically,
the
yes.
supremum for these two
Physically,
sets
never.
is 0.
You talk about that. You just do the wrong thing.
But from our set
few
on
misdemeanors
the
as
left
England
hand
Oh, yeah.
side,
Well, yes.
we have
I
the
was told
set which has only
Like
positive
that.
values,
be more
non-negative values.
accommodating at times.
And
in
since the
press
supremum is
conference.
0, therefore
Try and be more
the
tolerant
case
about
for
things that are
us
going on around
that
you.
is obtained from this equation is this one, because
Here, this is another long
the set
case
that
for
we are getting
sports.
from this equation, from the
Comical.
left hand side of this equation,
Just two.
is non-negative.
He played an out game.
And when the
in New
supremum
Zealand
of a non-negative set,
Wanganui.
the set of non-negative real
We got
numbers,
beaten
is 0.
by New Zealand.
When the supremum of the set of
went into the press conference.
non-negative real numbers
Conscious
is 0,
I've
then
gotta be
it obviously means that
more
the set
accommodating,
has only
more
one
polite, more
entity,
nice.
that is 0.
How have you
So the
found
set has only
Wanganui?
one element, that is
I saw
0.
it's a lovely park
So
ground.
it means that
And in fact, the lunches have been lovely.
the supremum
They're
is
really
0,
good.
then
Made a
the
good
element
effort.
is
Our
0.
pal John Etheridge.
This concept
One of
is
the
actually
nationals.
applied here.
England beaten. Coach enjoys lunch.
Hopefully you may have understood this concept.
Well, I think we both have
So
form
you
of
have
this.
just removed the supremum
It
sign
was here at
from
Lord's
here,
in '89 that I
because
left
the
the press
supremum of a
conference.
set
The theatre.
of non-negative
early
values is 0
on
if
Saturday
and
evening.
only if the element is 0. Instead of writing this, you may have to write some theory here.
Pakistan need 8. 56 for 1.
The supremum of non-negative of a set of non-negative real numbers, of a set of non-negative real numbers is 0
On the balcony,
if and
inside the
only
dressing room,
if
Trevor Bayliss might be a hint of a almost a grin behind there, but
the set
there is a lot to think about in terms of
As-
how to raise the performance levels over the next few days before they go to Leeds.
only one element.
England are absolutely 100% certain to be 1-0 down, with one to
That
play.
is 0. So
Full
I
toss.
try this concept here.
That's gone all the
We
way.
get the supremum of
Thrown back from the crowd. 2 to win.
absolute value of xij minus eta j
Well, Don Best might have enjoyed himself
is
at the bat
0
yesterday, and he
if and only if
batted with sterling qualities yesterday as well. But he's been picked as an off spinner. This has been a
xij
poor spell,
minus
actually.
eta
I know the
j
situation is
equal to 0.
very flat.
Note that
been a
we
poor
have
spell.
used the term if and only if
Your
here,
dilemma.
therefore we need not to prove the converse of this statement. Next, the absolute value of a number is 0 if and only if the element, the number is itself 0. We have used this concept many times in previous lectures, and from this xij minus eta j is equal to 0. Xij is equal to eta j, not equal to 0.
The full toss. And that's it.
So
Fabulous
from
effort
this,
from Pakistan. England
we get
looking thoroughly
this
dejected.
xij is equal to eta j. So
Young, inexperienced
the
team, well led,
sequence
well
of these
organised.
elements, because these
and they've
elements
done the
are
business.
same, therefore their sequence, the sequence that is
Full
formed
credit
from
to
these
Pakistan
elements,
for everything
Yes,
they've done
also
here at Lord's in this
these
opening
sequences
test
are
match
also
of the summer.
that's xij, the sequence of xij
They
is
have
equal to x,
outthought
the
and
sequence
outplayed
of
England
eta
in
j is
every
equal to
department.
y, so x is equal to
England will say that in the space of just over 3 days they've had one good session. That's completely unacceptable for
equal
a
to
home
y.
side looking to
So this
reset
was
after a
what
tough
we
winter.
had.
proof.
Mickey Arthur, as Pakistan's coach there,
The
is
next
entitled to
property
every
is the
smile
property
on his
M3,
face
which
and
is simple.
everyone else's faces in that
In this
dressing room. It's
property,
been
you have to prove
a great
that
example of
D of
making
X and
plans,
Y is
sticking to your
equal to D
plans,
of Y and
executing your
X.
plans, and winning a game, which
This is
you have
called
to
the
say,
symmetric-
looking back on it now,
symmetric
has been
property.
very,
J is
very
one of
one-sided.
Natural numbers.
Well, I think they've been
Absolute value
terrific,
of
Pakistan,
Xij minus theta j.
and they'll be thrilled with the performance. How often do you say Pakistan with a disciplined performance? Oh, it's been excellent. Varied attack, a leg spinner, a left armour, 3 quickies.
Since
Not
we know
that
that
many
we
people
can
in
write
today, but I'm sure that
absolute
they'll
value of
celebrate.
X minus Y is equal to
Winning in
absolute value of Y
3.5
minus
days,
X.
England winning the toss.
And I told you this in previous lecture, therefore
In 4 days' time, the next game,
this is equal to
starting on Friday up at Headingley.
Xij
Partnership of 54 there,
theta j
Imam and Harris.
minus Xij,
That's a dejected team with
which
lots
is
to think about.
definitely equal to D of Y and X. So we have proved the symmetry property.
All over
Similarly,
very
we have to
quickly.
prove the property M4,
Azhar Ali,
the
the
triangle
casualty
inequality.
ball by a,
For this, we have to
snorter from
introduce
Jimmy
a new
Anderson.
element.
Knocking them off, 66 for 1.
Let Z
Well, there won't be much to
Remember
report from the bowling
Allen
figures. Anderson, the wicket taker, just 3 overs, 1 for 12. It was a snorter, as you say.
Z is equal to
Disappointing, actually. Don Best there, given a
Zeta
chance
1
to see what he could do with the ball
Zeta
turning a
2.
little bit from wide of the
So,
off stump, the left-handers, but offline.
simply
Offline and length.
Zeta
Expensive for
J.
3.4
J is
overs.
equal to 1, 2, 3, 4.
And for England, well, they have
4.
problems in every department, so it's not just the bowling attack on this final
And it
day.
is bounded
Red Smith, the
sequence,
national
so absolute
selector,
value
some
of
brave
theta j
choices. He was seeing
is
some
less than
good news
or
there with the
equal
performance
to
of Joss Buttler, especially in the
D
second innings.
Z.
But whether you're the head selector,
Where
whether you're
D
England's
Z
management, whether you're captain,
Depends on
or
Z,
any
not
one of the
on
11
J.
involved in this
And
game,
it is the member
you know
of
you have some
zero.
serious questions to answer when that is the final result. Pakistan
Now
came to Lord's here for this
D
first
of
test of
X
2
and
in the
Y
series.
is
They
equal
weren't
to
expected to win, they
supremum
won
of
by a distance.
absolute value of Xij minus theta j.
Right, what we've got coming up. Rotherham versus Shrewsbury, the League
As
One
we
playoff
do
final, 2:30 on Sky
normally,
Sports Football, and
We
tomorrow
have to add and
League
subtract.
Two playoff, Coventry versus
Zeta J.
Exeter. That's at 2:30, Sky Sports Football. 2 good
Xij
games.
minus
And
zeta
today,
j
this is a crackerjack game.
plus
The Indian
zeta j
Premier League,
minus
CSK versus
zeta j.
Sunrisers Hyderabad in the final, 2 o'clock on
Make
Sky
this
Sports
pair
Mix.
as a number and this pair as a number and apply the property
done
of
it.
absolute
3.5
value.
days.
We have
Pakistan
this one
all the
is
way.
equal to or less than or
We'll be
equal
back
to the
very shortly with
supremum
David
of
Gower.
J member of natural numbers. Absolute value of Xij minus zeta j plus absolute value zeta j. So D of X and Y is less than or equal to supremum can be distributed over here. Supremum of J member of natural numbers. Absolute value of Xij zeta j plus supremum of absolute value of zeta j minus Xij. Xij absolute value. From this, we definitely have X and Y less than or equal to. This one is D of X and Z plus this one is D of Z and X. So hopefully you may have understood this whole question. The next one is the function space.
C of A and B. The next example is the function space, which is denoted with C and closed interval from A to B. The elements of this space are the functions, which are defined and continuous in the closed interval from A to B. The closed interval is from A to B, and the sign C, it actually represents that the functions in this space are the continuous functions. So how we will define the underlying set X here? Let X be a set of all functions let the functions be x and y and up to so on, and these are the functions of variable. For example, let we take the variable t, and these functions are defined and continuous on a closed interval from A to B, and let we say that this closed interval is J. Next we have to define a metric. Let the metric on X is defined by let we define the metric by d of x and y is equal to max, where max denotes the maximum of the absolute value of x of t, since x is the function of the variable t, minus y of t, where t is the member of the closed interval from A to B, that is J. So the maximum, it means that first we have to find out the difference between the function x and y at point t, and then we have to take the absolute value. We will have to keep doing this at different points of the closed interval from A to B. Then we will get a set, and we will have to find out the maximum value between them, and that maximum value will be denoted with this whole term. Next we have to check if this metric satisfies all of the properties of the metric. So all the first we will check the one. Obviously it satisfies the property M1, because the maximum of the values taken from the absolute values of x of t minus y of t, it is positive, because it is the maximum of the positive values, because we know that absolute value is always positive, it is real valued, and it is defined. Therefore, when you will take a maximum value from such values, then that maximum will again be a positive non-negative and real valued. Therefore, we can easily see that d of x and y is real valued, finite. Whenever we are saying that something is real valued or it belongs to the set of real numbers, it obviously means that that quantity is finite and it is also non-negative. So d of x and y satisfies the property M1. The next property is M2, in which you have to show that d of x and y is equal to 0 if and only if x is equal to y. Put the value of d of x and y, the maximum of the absolute value of x of t minus y of t, where t belongs to j, is equal to 0. Since this quantity on the left hand side gives a set of all non-negative values. If this set is 0, it means that the maximum value of the set is 0. So we will write that the maximum value of a set of non-negative values is 0 if and only if the elements of the corresponding set is 0. And we know that according to the definition of a set cannot possess two same values or two or more than two same values. So this set is actually this one, the set in which the only element is 0. This is one element set, and if you combine these concepts, then we will write that the maximum of t from j, maximum of x of t minus y of t is equal to 0 if and only if x of t minus y of t is equal to 0. And since we know that according to the definition of absolute value, the absolute value of a number is 0 if and only if the number itself is 0. So x of t minus y of t is equal to 0, and from this x of t is equal to y of t. So which means x is equal to y. Instead of x of t and y of t, we can just write x and y. Same as in the calculus, we can write instead of f of x, we can write it just f. So we need not to prove the converse because we are using the notation if and only if. The next the property is the property M3. It is obviously very simple. D of x and y is equal to maximum of t, which is taken from j maximum of x of t minus y of t absolute value. We have repeatedly used the property that I'm going to use here. We can write the above absolute value as y of t minus x of t, and which is equal to d of y and x. So d of x and y is equal to d of y and x. This was what we had to prove. The next one, the property M4. For this you will have to define a function. Let z of t be, yeah, it belongs to the space a and b, or instead of z of a and b we write just z of t belongs to x simply. D of x and y is equal to maximum of absolute value of x of y, sorry, x of t minus y of t. Add and subtract z between we have to add and subtract z minus z of t plus z of t and then minus y of t. Then according to the definition, according to a property, we can write it as absolute value of x of t minus z of t plus absolute value of z of t minus y of t. Since we have used this property for a number of times, therefore I'm not going to discuss this. You can distribute this maximum. So maximum of t member of j absolute value of x of t minus z of t absolute value plus the maximum of t member of j absolute value of z of t minus y of t. Thus it obviously means that d of x and y is less than or equal to maximum of absolute value of x of t minus z of t is d of x and z. Similarly, the next one is d of z and y. So this is the required triangle inequality. So we have shown all of the four properties of the metric, and this metric satisfies all these properties. Thus the the function space so defined is a metric space. The next and the final example of section 1.1 is the discrete metric space. The underlying set for the discrete metric space can be any set, and therefore there is no restriction on the form of the elements of X. They can possess any form. The discrete metric on X is given by d of x and y is equal to 0. The value of this metric is 0 if and only if x is equal to y. And if x is not equal to y, then the value of the metric is 1. And this is the reason why the name discrete metric is given to this metric. And obviously this is not a continuous function. Next, you have to prove that
the set X together with the metric D is a metric space. We will check if the discrete metric satisfies all of the property of metric. The property number 1 is M1, and it is obvious from the definition that the values of the metric are only 0 and 1, which are defined real valued and non-negative numbers. Therefore, t of x and y is real valued, defined or definite, and non-negative. Therefore, d of x and y satisfies the property M1. Next property is M2, which can also be seen from the definition. From the definition, of discrete metric, we can see that when we put x is equal to y, then the value of the discrete metric is 0. So from the definition, d of x and y is equal to 0 if and only if x is equal to y, which directly means that the property M2 holds. We need not to prove it because it is given in the definition. Next one is M3. So when x is not equal to y, then d of x and y is equal to 1, and similarly d of y and x. Since x and y are not similar, therefore the discrete metric will give you the result 1. From these two equations, we have d of x and y is equal to d of y and x. The next property that we have to prove is the triangle inequality, which is M4. For this, you have to suppose that let Z be the member of X. X, Y, and Z all are member of X. Then d of xz is definitely equal to 1 if x and z are not equal, and d of z and y, this is again equal to 1. Okay, since d of x and y is equal to 1, and we know that 1 is less than 2, and 2 can be written as 1 plus 1, so d of xy is less than 1 plus 1, and this one, the first one, can be replaced with this equation, and the second one can be replaced with this equation, and therefore we have d of x and y is less than d of x and z plus d of y and z and y, sorry. We have one thing short, that is the equality sign. The equality sign holds if x and y and z are all equal. So we will write that if x is equal to y and y equal to z and x is equal to z, then equality holds because everything becomes 0. We know that if x is equal to y, then the right hand side is equal to 0. Similarly, if x is equal to z, then this quantity is 0. If z is equal to y or y is equal to z, then third term is 0, and we will get 0 is equal to 0 plus 1, 0, which is again equal to 0. So it means that the equality holds if x and y and z are equal. Then
d of x and y is equal to d of x and z plus d of z and y. Name it as the inequality 1 and name the second as the equation number 2 and combine them together. You'll write here, by combining equation 1 and 2 we get d of x and y is less than or equal to d of x and z plus d of z and y. And in this way the inequality property, the triangle inequality holds, and therefore the discrete metric space is a metric space. Hopefully you may have learned something from this section. Thanks for watching.